To our next unit, right triangle trigonometry, which is a fancy way of saying we're going to be dealing with a lot of triangles this section. Last unit we dealt with showing triangles congruent to each other. This time we're going to look for a lot of relationships within triangles and kind of expand on our knowledge of similar triangles to find relationships in triangles with specific angles and find a relationship between the angles and the side lengths. But before we get to any of that, our objective for this first section is simply simplifying radicals. So our objective is going to be to express radicals in simplest form. So a radical is anything that uses this sign, this radical sign. This number that's up here in front of the radical, kind of in front into the upper left here, is sometimes referred to as the degree, sometimes referred to as the index. The index is also a term we'll use to refer to that number. The number under the radical sign is called the radicand. That's the number we are taking the root of. So radical is also sometimes referred to as a root or root, depending on the region. Sometimes I'll say root, sometimes I'll say root, because I'm from several different places. So index or degree, radical or root, and radicand. And since the radical that we're most familiar with is the square root, the second degree root, we're going to start off by listing off what are called the perfect squares. These are numbers that when you square the integers, you get these numbers. So 1 squared is 1, 2 squared is 4, 3 squared is 9. We just can square each of the integers to generate our list of perfect squares. So 1, 4, 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, then we have 49, 64, 81, and then 100. Now, all we're prompted to here is to go from 0 to 100. Those are the ones that show up most frequently, but we could keep going if we wanted. 11 squared, 12 squared, 13 squared, 14 squared, 96, and 15 squared, 225. Past that, that's as far as I have memorized off the top of my head. Sometimes we'll encounter ones that show up frequently enough to know, but really up to 100 is usually enough. Now, when we take the square root, the rule we're going to be relying on is that when you multiply square roots together, that's the same thing as multiplying the two radicands under the radical sign. And when you take a root times itself, square root of x times the square root of x, or the square root of x squared, you get just x. Squares and square roots are inverse operations. This, of course, is only true as long as x is greater than or equal to 0. So over here when we see root 2 times root 8, we can multiply those square roots together to get the square root of 16. Multiply the square roots together, multiply the numbers under the square root. 2 times 8 is 16. And then 16 is on our list of perfect squares. It means that when we can use this rule here, the square root squared, this root 16 can also be written as the square root of 4 squared. Right? 4 squared is 16, so that's just 4. Now, you don't have to necessarily write this in between step. The square root of 16 is 4. So when we have a combination of numbers that aren't under a radical sign and numbers that are, we can multiply the stuff that's under the radical sign, and we can multiply the stuff that's outside the radical sign, but not together. So 2 times 3, this 2 and that 3 gets us 6. So this 2 and that 3. This root 3 and root 4, we can multiply together to get the square root of, and actually, I'm going to make this a little bit easier on ourselves. 4 is already a perfect square. So I'm going to do some rearranging here. So this is a 2, root 3, 3. This 2 is, or this square root of 4 is 2. So all the stuff that's outside the square root now. 2, 3, and 2. 2 times 3 is 6, times 2 is 12. And root 3 times root 12 is the square root of 36. We can multiply the stuff that's under the square roots together. And then the square root of 36 is 6, so we have 12 times 6, which is 72. And then the square root of 5 times the square root of 5 is the square root of 25, which is just 5. Okay, so we're looking to get those perfect squares under the radical. Sometimes it works out really nicely like this. Sometimes we're going to have to separate out the factors in order to simplify. So in this case, all three of our numbers here ended up being whole numbers. We were able to take the square roots of those perfect square factors. We'll do these ones, the guided practice, we'll do those in class together. I just wanted to have some examples to go off of. So this next one, it doesn't seem like there's any operation going on, so we're going to just simplify what's under there by splitting this up into its factors. We want to look for a perfect square factor that goes into 90. So our goal to know that it's simplified is no radicands have perfect square factors other than 1. No radicands are in the denominator, and the radicands are all integers. So this 90 here, if I'm looking at my list of perfect squares, start at the bottom and go up. We don't need to worry about 1, because 1 divided by anything is still itself. 90 is divisible by 2, but not 4. 90 is divisible by 9. Let's try 9. So the square root of 90 can be rewritten as the square root of 9 times the square root of 10. Right? 9 times 10 is 90. And 9 is a perfect square, so we can take the square root of 9. The square root of 9 is 3. And the square root of 10, well, 10 is not a perfect square. It's going to stay under the root sign. So radicands have perfect square factors. Well, the 10, its only factors are 2 and 5, not perfect squares. So these, the 3 square roots of 10 is equivalent to 90. We're done. With 120, once again, look for a perfect square factor. 4, I know, goes into 120. Let's see how many times. So 4 goes into 120. We could write this as the square root of 4 times the square root of 30. And then we have square root of 4 is 2. And 30, let's see, its factors would be 6 and 5. 6 factors into 2 and 3. So 2, 3, and 5, none of those are perfect squares. We don't have any repeated factors, so we are done with that, 2 root 30. With the 210, look for a perfect square factor of that. Let's see, does 4 go into that? Let's see, 2 goes into 210. 105, nope, not that. Let's see. If we get stuck and we're not sure like what factors are going to work, we can just start listing off factors that we do know that aren't perfect squares. So like 2 factors into 105, 105 times. 105, 3 is a factor of that. Let's see, 3 is a factor. Let's see. I don't have my calculator on me. If I back this up, 21, 3 goes into 21 7 times. So that'd be, maybe I can get this to be smaller. So 3 goes into that 70 times. Okay, then that 2 times 35. 35 factors into 5 and 7. So 3, 2, 5, 7, those are all prime factors. None of them repeat, and we don't have any perfect square factors. So actually the square root of 210 does not simplify any further, so it's already simplified. Okay, so the square root of 210 is already simplified. Okay, it can only simplify if it has perfect square factors that we can actually take the square root. So radicand has no perfect square factors. Good on that. No radicands in the denominator. Well, there's no denominator. And radicand is an integer. Cool. Done. So we'll do those other 3 in class together. Let's do some more practice. The smallest perfect square that you can find is not always the one that's going to work. For instance, square root of 32. 4 does go into that 8 times, so it factors into 4 and 8. Square root of 4 is 2, but 8 still has a 4 that goes into that, so it can simplify further. So we can do this in 2 steps. We could write this as 2 root 8, and then the 8 we can further simplify into 4 and 2. Square root of 4 is also 2, and that 2 that's under the square root stays under the square root. We can multiply those 2's that are outside the root. We can multiply those together. 2 times 2 is 4, so 4 root 2. Now I say there's another way to do that. As soon as you realize that 4 goes into that 8 a second time, you can multiply the 4's together and find an even bigger perfect square that goes into 32, 16. So the square root of 32 can be written as square root of 16 times the square root of 2, and the square root of 16 is 4. And we find our simplified radical equivalent to what we get the other way, but get it one step sooner. Always check to see if the numbers are perfect squares themselves. We could evaluate the square root of 625 and find that that is in fact 25. If you don't realize that right away, we can try dividing 25 into 625 and find that 25 goes into that 25 times, and then, oh yeah, we got 2 25s, 5 times 5 is 25. So the square root of 625, just evaluate that, and it's 25. Square root of 200, 100 goes into that. 100 goes into that 2 times. And then the square root of 100 is 10. And the 2 that you can't take the square root of, it's still trapped under that radical sign. It stays there. 28 can factor into 4 and 7. 2 root 7 would be our simplified radical. So any parts that aren't perfect squares are trapped. They stay under the square root sign. If it is a perfect square, we can take its square root. For 68, 4 goes into that one. 4 goes into that one. Let's see. Is that 17 times? 17 times? Yes. And so it'd be 2 root 17. So we can take the square root of 4, we get 2, and then the 17 is stuck under there. Same thing with 60. 4 goes into 60 15 times. Square root of 4 is 2. 15 stays under the root. Okay. We'll wrap those last couple ones up in class together. But I want to talk about another type of example here. And it's ones where we have to look out for radicands in the denominator, or fractional radicands. So radicands need to be integers. So here we have this 2 over root 6. We can't keep a root in the denominator, but we can use the fact that the square root of a square, the square of a square root is just the number. Square of a square root is just the number. So to get the 6 out of the square root in the denominator, we can multiply by the square root of 6. But I don't want to multiply by something that's going to change the value of the expression. So I'm also going to multiply in the numerator, because anything over itself is 1. Root 6 divided by root 6 is 1. And multiplying by 1 doesn't change the value. Something times 1 is still itself. But it is going to let us change where the square root's at. So 2 root 6 on top. You can't multiply something that's outside a root, something that's in a root. And on the bottom, root 6 times root 6 is just 6. And then now that the 6 is outside the square root, it's free to interact with that 2. 2 over 6 reduces to 1/3. So we end up with a 3 in the denominator. 1 times root 6 is just root 6. So root 6 over 3. For the square root of 25 over 20, we could actually simplify first. It might be tempting to take the square root of 25 to begin with, because it's a perfect square, but we're going to be left with a square root in the denominator, and we don't want that to happen. So I'm going to instead simplify this. 25 over 20, we could take a 5 out of both of those. 5 comes out of that 5 times, and 5 comes out of that 4. So we have the square root of 5/4. So the square root of 4, we can take the square root of that. Square root of 4 is 2. So it's no longer under the square root sign. Just like with, I'm actually going to rewrite this. Just like with multiplying square roots, anything that's, when you divide square roots, you can take the square root of the numerator and denominator separately. So square root of 5 is going to stay on top. Square root of 4 is 2. So square root of 5 stays on top. With this one, the square root of 5 over the square root of 18, we can multiply top and bottom by the square root of 18 to get that square root out of the denominator. But we can actually make this a little bit more interesting, or make the numbers a little bit nicer first by simplifying the square root of 18. So I'm going to actually rewrite this. Square root of 5 stays the square root of 5. Square root of 18, 9 goes into that. The square root of 9 goes into that twice. So we have the square root of 5 over the square root of 9, which is 3, root 2. And now it's just the root 2 that I got to get rid of. So multiply by the square root of 2, multiply by the square root of 2 on top and bottom. So root 5 times root 2, you can multiply within the roots to get root 10. 3 times root 2 times root 2, we can multiply the root 2's together to just get 2. So remember, when you multiply a root times itself, that square root squared is just the number under the root. Okay, so root 2 times root 2 is just 2, and then 3 times 2 is 6. So we have a square root of 10 over 6. And while one thing is under the square root and isn't simplifiable, the other thing is not under the square root, so those can't interact. So even though 10/6 would reduce, the square root of 10 over 6 does not, because the 6 is not under the square root sign. But that was our goal, to rationalize the denominator. No radicands in the denominator. And then on this last one here, 2 over 30 root 2, same deal. Multiply by root 2 on top and bottom. And 2 times root 2 is 2 root 2. And down here, 30 times root 2 times root 2. Root 2 times root 2 is just 2. And now that that's out of the square root sign, it's free to interact with the other part that's out of the root sign. 2 divided by 2 is just 1. So we have the square root of 2 over 30. Square root of 2 over 30. We'll revisit this again when we do the guided practice in class. We will also tackle this bottom bit in class. Has some mixed review of what we were just talking about. So we'll talk about that more in class together. We'll tackle those guided practice problems and check to see what questions we have. Talk to you then. Bye for now.